So starting with our excessive hydrogen ion in the filtrate, it binds with bicarbonate ions already present in the filtrate because of CO2 or metabolic bicarbonate ions. I'm going to circle this so you can follow it. It forms bicarbonic acid, all right, which dissociates into water and CO2. Notice the hydrogen itself isn't actually going over to the filtrate, okay? But our CO2 does. Meaning that it can't go back and form carbonic acid. And we're going to return the CO2 with the hydrogen component over here. So now the CO2 plus water already in the cell, using carbonic anhydrase, forms carbonic acid. That dissociates, as we saw over here, to form a hydrogen ion and to form a bicarbonate ion. Hydrogen ions can move out of the tubular cell into the filtrate via 3 different mechanisms. Okay. So these are on this slide. The first one that's shown is an antiport secondary active transport. Remember, we moved glucose out of the filtrate via a symport. Glucose was going down its concentration gradient, and sodium was going down its concentration gradient, so both of them moved much more readily. This is an antiport. Hydrogen ions are going against their gradient, because we typically have already an acidic pH. But because of the energy source from our sodium-potassium pump that you see up here, so that's our sodium-potassium pump that's using ATP and using up the energy to provide that strong gradient of sodium moving into the cell. So that's where we get the energy for sodium to move this antiport pump. Sodium goes into the cell, and hydrogen ions are moved up their gradient out of the cell. Okay, so that's one mechanism. I'll write this here. Secondary transport via sodium, hydrogen, antiport. All right, that's one. Another mechanism is the hydrogen can just be pumped out via a hydrogen pump. Doesn't have ATPase up there, but that's what it's referring to. And then a third is going through a symport channel with chloride. So both chloride and this is a and there's several different proteins that are functional here. So we have co-transport, a symport transport.
Is chloride going in or out?
It's going into the filtrate.
Secreted, right?
Mm-hmm. Now, once the hydrogen is in the filtrate, filtrate, we have a very, very, very low pH. We talked about this yesterday. Any of you have ever thrown up, it burns, okay, because of the low pH. We don't want it feeling like that every time we go to the bathroom. And so our pH of our urine is around 5 to 8. So obviously it's not the 1 to 2 that we see in hydrochloric acid of the stomach. And so we have buffering systems. And the two important buffering systems are phosphate and the ammonium ion. So the hydrogen can bind to ammonia, which is one of our byproducts of urea and amino acid breakdown, to form the ammonium ion. And here, even though it's not within a cell, we see the importance of the phosphate buffer. So those are the two most important buffers of the filtrate. Okay? Now rather than complicate that, oh, I need to get rid of bicarbonate ions. So bicarbonate ions have a channel in the basolateral membrane that typically exchanges them with chloride or with sodium. Okay? We have an anion exchange, and then we have a co-transport with sodium. So those are how bicarbonate, those are found in the basolateral membrane. That's why the basolateral membrane is permeable to bicarbonate ions, but we don't have these forms of transport for hydrogen in the basolateral membrane, so it's not permeable to hydrogen ions.
Bicarbonate's moving this way.
Out. The bicarbonate is moving. Now remember, this is not a new bicarbonate. All we're doing is replacing the carbon that we transported over via diffusion of the gas.
I can see why it's called basal. Why is it called lateral? The basolateral?
They're very similar. The lateral is up here, and the same thing happens in the lateral. So they're described as the same kind of component. Okay? So that's how we add hydrogen ions to the filtrate. So this would be hydrogen ion secretion. Now, I'm going to erase it. On that board, I drew it on the same cell. Okay, but I'm going to erase it, and now we're going to move bicarbonate ions, new bicarbonate ions, to the blood. We're going to put new bicarbonate ions that were in our filtrate in the blood. Okay? So may I erase this? Okay.
Is that bottom one a filter?
Yes.
I'll get a picture of that.
Now we have bicarbonate ions that are in the filtrate because they were filtered. And we're going to move them back into the blood, so that is bicarbonate ion reabsorption. Bicarbonate ions don't have any transport channels in the apical membrane, in the microvilli. So we have to convert it to carbon dioxide. Okay? So this plus a hydrogen ion forms carbonic acid that dissociates to form water and CO2 which diffuses into the cell. CO2 interacts with water in the cell, forms carbonic acid, returns the hydrogen back to the water, and sends bicarbonate ion, a new bicarbonate ion that the blood has not had before, to the blood for buffering. Okay? But it uses the same channels. So rather than draw those all over again, see hydrogen channels, the bicarb channels in the previous diagram. Okay? But it's a new bicarb. It wasn't in the blood before. So now we've taken hydrogen from the blood and we've added bicarb, so we have elevated our pH through two different mechanisms. Now this is the primary mechanism by which the body adjusts an acidic pH. What happens if we have an alkaline pH? We wouldn't want to reabsorb more bicarb, and we wouldn't want to get rid of hydrogen. So if the body is in acidosis, and again, whether it's in respiratory acidosis or metabolic acidosis, this will take effect. If the body is in alkalosis, this stops. Okay? We keep the hydrogen ions because we need them to lower a pH that's too high. And we don't take back bicarbonate ions because we already have too many. So we activate this process, hydrogen secretion and bicarb reabsorption when the body is in acidosis, and we stop this process when the body is in alkalosis. Okay? However, listen to those words in lecture. However, also known as, and that's what teachers always test on, right? The exception. So, that's where I want to go. So, in the collecting duct primarily, we have type A intercalated cell. Well, this will give you and collecting duct. We have type A intercalated cells, and that this functions in the same fashion as proximal convoluted tubules. Here's another illustration. So over here is the filtrate. It's called urine, but it's really filtrate. All right. And so we are going to be secreting hydrogen ions into the filtrate and reabsorbing bicarbonate ions. So this is going to be what's called the intercalated cell type A. It's intercalated between the principal cells of the collecting duct. Type B, notice what's happening instead. See, here it stands for carbonic anhydrase. Type B is secreting bicarbonate ions and reabsorbing, up there on the red channel, hydrogen ions, which is just the opposite. And that's because the channel proteins are on the opposite side. This guy has a bunch of protein names that we haven't gone through, but you can still see the same event. So in the type B intercalated cell, bicarbonate ions are going into the filtrate, and hydrogen ions are going into the blood. Yes?
So do we have these channels on both sides just based on whether we have acidosis or?
No. These would be so if you are in acidosis, the channels don't move. If you are in acidosis, yeah. If you are in an acidosis, then the type A intercalated cells and the proximal convoluted cells would be functional.
So there's just different cells.
Right. If you are in alkalosis, type A cells and the proximal convoluted cells wouldn't function, and type B cells would function. And again, it's concentration. It's because of where more of the ions are located. Okay. So I just want you to recognize that intercalated cells type B would secrete bicarbonate ions and reabsorb hydrogen ions. And that's the opposite of what we've just gotten through talking about. So we do have some cells that do that, and it's because they have these channels on the opposite membranes. All right, so now let's look at more general concepts of acid-base balance. And in your lecture notes, I talk about the ratio of the bicarbonate ions and carbon dioxide ions. So this is on page 64 of your lecture notes. Unfortunately, I should have put my Henderson-Hasselbalch equation in there, but that's in your lab packet, and I'll go over that in just a moment. In the Henderson-Hasselbalch equation, which I didn't save, I put it on here and I didn't save it. I'll leave it up there for just a moment. So I'm going to put that here. This is a way of looking at the relationship between acids and bases and determining the pH. So we have the amount of acids, the amount of bases, the ratio between that. We also utilize the binding affinity. It's called the pK, all right, between the hydrogen ions and the hydroxyl groups. And that changes with temperature. So when we're talking about the acids and bases that we utilize to determine the ratio in human physiology, is we look at the ratio of bicarbonate ions, that's reflecting our base content, to the amount of carbonic acid. And that obviously is reflecting the acid. The pK for this is 6.1. pK and the binding affinity between hydrogen and the movement back and forth between these components. So the Henderson-Hasselbalch equation says the pH is equal to the pK plus the log of the base divided by the acid. So our base is bicarb and our acid is carbonic acid. So our pH is equal to 6.1 plus the log of that, whatever that is. And it's going to vary depending on our conditions. So without putting in actual, well, normal bicarbonate levels in the blood, arterial blood, is about 24 milliequivalents per liter, I believe. That's bicarb. And normal PCO2 is 40 millimeters. Well, that didn't say PCO2, right? That says carbonic acid. So to convert the PCO2 to carbonic acid, we have to multiply this by a factor. That's going to give us our carbonic acid value. When we look at this ratio, the amount of bicarbonate, because remember, why is that ratio important? Because we have to buffer those molecules. So the carbonic acid is going to dissociate and give us hydrogen, and those hydrogen ions will bind to the bicarbonate, neutralize them. So when we look at the normal ratio of bicarbonate to carbonic acid, we come out with a ratio of 20 to 1. That's an important number. If we take the log of 20, just plug it into your calculator and hit log, all right? And we add it to 6.1, we come up with a pH of 7.4. That's why the 20 to 1 is so important. The 7.4 is smack dab in the middle of our range of 7.35 to 7.45. Remember again, the 20 stands for what substance? How much base we have, how much bicarb we have. The 1 stands for our respiratory, how much carbonic acid we have. All right? So we're going to look at the types of conditions that would be reflected in those changes of 20 to 1. Remember, when we take the log of 20, it gives us our normal pH of 7.4. pH 7.4 is equal to 6.1 plus the log of 20 to 1. So 20 to 1 is the normal ratio of bicarbonate ions to carbon dioxide, as reflected by carbonic acid. Okay. What happens then, what would you expect would happen to our pH if, let's say that, again, go back to vomiting, and we throw up our hydrochloric acid, which means we're not absorbing our hydrogen ions. Our bicarbonate numbers would be normal, but we wouldn't have enough hydrogen ions to buffer them. So in essence, we would see a condition that looked like this. Notice what changed. The bicarbonate ions were higher, our ratio is greater than 20 to 1, and our bicarbonate ions are too many. So would our pH be too high or too low? Too many bicarbonate ions, not enough hydrogen ions. Too high. So this condition is known as alkalosis. Okay? So when the ratio is greater than 20 to 1, you have alkalosis. Here's another condition. My bicarbonates are fine, but I've been breathing off too much CO2. I've been hyperventilating. So now I have the normal amount of bicarbonate ions, but not enough carbonic acid to create sufficient hydrogen ions. My ratio is still greater than 20 to 1. It's really now 40 to 1. All right? So this condition is still alkalosis. Here, my bicarbonate number changed. Here, my carbon dioxide number changed. Okay? So if my PO2 instead of my PCO2 was 55, instead of, the other way, if my PO2 was supposed to be 40 and it was 30, I would see this number decrease. All right? So now, because of the which number changed, the bicarbonate or the carbon dioxide number, I can now identify the cause. In this case, my cause is metabolic. I was throwing up. I got rid of hydrogen. I have too many bicarbs because I don't have enough hydrogen. So I have too many unbuffered bicarbonate ions is basically what's being shown here. Right? Here, it's respiratory. Sorry, one. This is a respiratory alkalosis. I have a normal amount of bicarbs, but too many for the amount of hydrogens. I don't have enough hydrogen ions. So it's still alkalosis because I have too many bicarbs, but the cause is I breathed off too much CO2. So I'm not forming enough carbonic acid. Does that make sense? You can interpret that. All right, now let's change the numbers. And now I have 15 to 1. Normal amount of CO2, but I've lost bicarbonate ions. Maybe diarrhea. I got rid of all the bicarbonate ions from my pancreas instead of reabsorbing them back to my body. So I have a normal amount of hydrogen ions in my body, but not enough bicarbs to buffer them. And so this condition, which is a ratio of less than 20 to 1, is going to give me acidosis. What would respiratory acidosis look like? I'd have my normal amount of bicarbs.
Over 1.
Too many carbon dioxide molecules. So I don't have enough bicarbs to buffer the hydrogen. So this would be acidosis. Again, this would be metabolic acidosis, and this would be respiratory. Acidosis.
Respiratory alkalosis from hyperventilating or?
Uh-huh. Yeah. That's the most common cause. Okay. Now, let me throw a curveball here, or a monkey wrench, or whatever. What's going on here? Exactly. Someone's been reading ahead.
What did she
All
say?
right.
What did she say?
Compensated. So what does compensation mean? What happened when I had pneumonia? What happens to my CO2 level? It goes up, all right? CO2 level is 2.0. What do my kidneys do if my CO2 level is really high? Do I reabsorb bicarb or do I secrete bicarb? I reabsorb it. So instead of 20, my bicarb level is going to go up. Compensation. Okay? Here, I vomited again. Got morning sickness.
Oh, wait a minute.
I lost my hydrogen ions, and now I have too many bicarbs without the hydrogen ions to buffer them. Or maybe I just took an overdose of Tums. So now I have too many bicarbs. What's my respiratory system going to do to compensate?
Decreased respiratory.
Decrease respirations. My CO2 goes up. My carbonic acid goes up. Okay. So this would be alkalosis, because I have too many bicarbs.
Metabolic.
This would be acidosis, because I don't have enough bicarbs. How do I determine the cause? Here my ratio is greater than 20 to 1. Here my ratio is less than 20 to 1. But how do I know if it's respiratory or metabolic? The one that changed the most. All right, this is a 20% change. This is a 50% change. Okay, actually more than 50%. 50% change would be 30. So it's supposed to be 20, half again as much would be 30. So it's a 75% increase in my bicarbs. This is only a 20% increase in my carbonic acid. So the one that changed the most is the cause. The other one changed to try to catch up. So this is now then respiratory alkalosis with partial
I got this all wrong.
compensation. Okay? Here, I've only increased my bicarbonate ions by 20%, and I've increased my carbon dioxide by 100. I've doubled my carbon dioxide, I've only increased this by 5, that's 20%. Yes.
On your first example of respiratory alkalosis, the bicarb didn't change at all.
That's because I was focusing on the cause. There's no compensation there. So that's my normal bicarb. All that I did was hyperventilate. I have no compensation. My pH is going to be much lower here without that compensation. Okay? And to determine pH, you would follow that formula. You would take 20 divided by 0.5, which would give you 10. You would take the log of 10, add it to 6.1, and that would be your pH. That's going to be a much lower number than this number. This number, wherever I am, that number, because I have compensation. Okay? So here it's going to be
Metabolic.
did I say respiratory?
Yeah.
I'm sorry.
That's what I
That's what you're talking about, no wonder.
Okay.
Someone got ahead. Okay. Here we have respiratory acidosis. Sorry about that. So 35 is more change than 1.2. 25 is not as much, this is double. So my cause is respiratory, again, with partial compensation. My pH is better than it would be, but it's not back to normal. Okay, what if I have a number that looks like that? My ratio greater than 20 or less than 20 to 1?
Greater.
Yeah,
Greater?
it's the same.
It's exactly 20 to 1.
Yeah.
Half of 20 is 10, half of 1 is 5. So I've increased each by the same amount. This is full compensation. My pH is 7.4.
I am totally lost right now.
What's the cause? I have no idea. I don't know which one changed.
Itself, so it doesn't
I don't know
matter.
which one changed first. Okay? So the cause can't be determined. I don't have normal amounts, but my pH is normal because they both have changed the same amount. Okay? All right. Couple more minutes. Just wanted to show you
1244.
on the extra credit in lab. So this discussion of the Henderson-Hasselbalch equation is in your lab packet. Thank you. Page 53 is the homework assignment, well, extra credit. And so there are 3 sets of problems. 3 sets of individuals in each set of problems. So for this, we're using the same numbers for this. So this individual, here's our Hasselbalch equation, pH equals 2K plus log of, remember you have to multiply your carbon dioxide to actually get it to the carbonic acid form. So Jackie's PCO2 is normal. What about her bicarbonate ions? They're supposed to be 24. So they're elevated. So would you expect her to be in alkalosis or acidosis? Alkalosis. What's the cause? Metabolic, because her CO2 didn't change. Okay? Now to find out what her pH is, and we would expect an elevated pH, you plug this into the equation, multiply the 38 by 0.03, multiply the 40 by 0.03, divide the 38 by that number, you come up with 31.67, take the log of that. Now if you have a logarithmic calculator, you just punch the log button. You can go online, look for free online logarithmic calculators, you type in your number, you hit log, and it gives you the answer. If you want anti-log, you hit anti-log. If you have a calculator, the anti-log is usually the function above. You have to hit the function button, and then the log, and it will take the anti-log for you. So these are pretty basic, these first ones, and you have a pH of 7.6, which is alkaline, what we expected. All right, now using those same numbers, the next type of questions, I give you the pH, and I want to know how much bicarbonate ion. What's your bicarbonate level going to be? So for these the next 2 sets, you need to do anti-log. And notice you're solving for the anti-log on both sets. You're solving for the anti-log of the pH minus the pK. So we know her pH and we know her carbon dioxide. So this would be X. The anti-log of the pH minus the pK times her carbonic acid component.